The James Webb Space Telescope has found galaxies that are too big, too bright, and too structured to exist at the point in cosmic history where we are seeing them. That single observation is not a minor puzzle. It is a direct challenge to the most successful cosmological models scientists have ever constructed. To understand why this matters, you first need to understand what astronomers actually expected to find when they pointed the most powerful space telescope ever built toward the farthest edges of the observable universe. The expectation was simple. Look back far enough in time, and you should see the universe in its infancy. Dim, chaotic, patchy. Early galaxies should look nothing like the elegant spirals and massive ellipticals we observe nearby. They should be small, irregular, and slowly accumulating mass over long periods of time. The logic was sound, and it came from decades of careful theoretical work and observational confirmation. Instead, what Webb found has prompted serious conversations at the highest levels of cosmology about whether our fundamental picture of the universe needs to be revised. Let us start at the beginning, or at least what we currently believe the beginning was. About 13.8 billion years ago, the entire observable universe was compressed into an extraordinarily hot, dense state. In the first fractions of a second, energy and matter were indistinguishable. As the universe expanded and cooled, fundamental particles formed, then atoms, then over hundreds of millions of years, gravity pulled that matter together into the first stars and galaxies. This story is encapsulated in a framework called the Lambda CDM model. Lambda refers to the cosmological constant, the mathematical term Einstein originally introduced and later abandoned, which we now use to describe the behavior of dark energy. CDM stands for cold dark matter. Together, these two mysterious ingredients, a form of invisible matter that interacts gravitationally but not electromagnetically, and a form of energy that drives the accelerating expansion of space, form the backbone of modern cosmological theory. Lambda CDM is not just a rough sketch. It is a precisely calibrated framework that has successfully predicted an enormous range of observations. It correctly describes the distribution of galaxies across cosmic time. It accurately predicts the pattern of temperature fluctuations in the cosmic microwave background. It accounts for the large-scale structure of the universe, the vast network of filaments and voids that astronomers call the cosmic web. For decades, every new telescope and every new measurement seemed to confirm it. Then the James Webb Space Telescope began operating in earnest, and the confirmations started running out. Webb was designed from the ground up to look further back in time than any previous observatory. Its primary mirror stretches 6.5 meters across, nearly 3 times the diameter of Hubble's. More importantly, Webb operates primarily in the infrared. This is critical because of a phenomenon called cosmological redshift. As the universe expands, light traveling through space gets stretched. Photons emitted by a distant galaxy as visible or ultraviolet light arrive at our detectors, shifted toward longer, redder wavelengths. The farther the galaxy, the more the light has been stretched. The most ancient galaxies, those that formed when the universe was only a few 100 million years old, have had their light redshifted so severely that by the time it reaches us, almost none of it remains in the visible spectrum at all. It has all been pushed into the infrared. Hubble, an optical and ultraviolet telescope primarily, could barely detect these objects. Webb, optimized for infrared, can see them clearly. And what it is seeing is deeply puzzling. One paper published in the Astrophysical Journal reported the identification of 87 candidate galaxies that appear to have existed between 200 and 400 million years after the Big Bang. This is an astonishingly early moment in cosmic history. To put it in perspective, if the entire age of the universe were compressed into a single calendar year, these galaxies would have appeared before the end of the first week of January. The problem is not just that they exist, the problem is what they look like. These objects are not the primitive, dim, irregular structures that theory predicted. They are bright, massively bright. They contain enormous numbers of stars, tightly packed, in configurations that suggest an advanced stage of galaxy development. Some of them appear to have already converted nearly all of their available gas into stars, a process that, according to current models, should take billions of years. Think about what that means in concrete terms. A typical galaxy converts roughly 10% of its available gas into stars over its lifetime. The rest remains as swirling clouds of gas and dust, slowly feeding new rounds of star formation over billions of years. What Webb appears to be observing is something more like a galaxy that converted nearly 100% of its available material almost immediately. No leftover gas, no reservoir of raw material. Just immense concentrations of stellar energy shining from the earliest pages of cosmic history. This should not be possible under Lambda CDM. The reason comes down to what physicists call the matter-power spectrum. In the early universe, matter was not distributed evenly. There were tiny fluctuations in density, regions slightly more compressed than others. Over time, gravity amplified these fluctuations. Denser regions attracted more matter, grew denser still, and eventually collapsed into stars and galaxies. But this process takes time. It has a speed limit set by the fundamental physics of gravitational collapse, gas cooling, and the competing pressure of radiation. Under Lambda CDM, the amount of matter that could have collapsed into stars within just a few 100 million years of the Big Bang is tightly constrained. There simply was not enough time, given the physics we understand, to build galaxies as massive and developed as the ones Webb is finding. Astronomer Haojing Yan, who led one of the key studies of these early galaxy candidates, was direct about the implications. Even if only a fraction of the candidate objects are eventually confirmed as real galaxies at the distances Webb appears to be detecting them, the discovery forces a serious rethinking of galaxy formation theory. But before we conclude that Lambda CDM is broken, there are important caveats to work through. First, these are still largely candidate galaxies. Confirming the true distance of a galaxy requires spectroscopy, the detailed analysis of its light to identify specific chemical signatures at known wavelengths. When those signatures are shifted to longer wavelengths, you can calculate precisely how far the light has traveled, and therefore how far back in time you are looking. Some of Webb's early detections were based on photometry alone, the brightness of the object across different wavelength bands, rather than full spectral analysis. Photometric redshifts are estimates, and some fraction of objects initially identified as very distant may turn out to be closer, unusual objects that mimic the appearance of high redshift galaxies. Follow-up spectroscopic observations are ongoing, and some of the most extreme candidates have already been confirmed at their extreme distances. The galaxy JADES GSZ 140, for example, was confirmed spectroscopically as existing when the universe was approximately 290 million years old. It is not only remarkably distant, but also surprisingly bright and chemically complex for an object so early in cosmic history. Second, some theorists have proposed modifications to known physics that might allow for faster early galaxy formation without abandoning Lambda CDM entirely. If star formation efficiency in the early universe was dramatically higher than in the present-day universe, perhaps because early gas clouds had different compositions or temperatures, then you might be able to squeeze more stellar mass out of the available material more quickly. Some simulations suggest that a transient burst of extremely efficient star formation in the earliest structures might account for some of what Webb is seeing. Third, there are proposals involving the nature of dark matter itself. Standard cold dark matter consists of particles that move slowly and clump together in particular ways, forming the cosmic scaffolding around which ordinary matter assembles into galaxies. But alternatives exist. Warm dark matter, fuzzy dark matter, interacting dark matter. Each of these hypothetical variations would produce somewhat different large-scale structure and might allow for different patterns of early galaxy formation. None of these alternatives has yet been confirmed observationally, but the anomalies Webb is finding are giving theorists new motivation to explore them. To fully appreciate why these early galaxy discoveries are so disruptive, it helps to understand the broader story of what the universe looked like in its first billion years. After the Big Bang, the universe went through a period of extreme heat and density. Matter and radiation were locked in a tight, opaque plasma. Photons could not travel freely. The universe was effectively a glowing fog. This lasted for roughly 380,000 years, until the universe had expanded and cooled enough for electrons and protons to combine into neutral hydrogen atoms. When this happened, the fog cleared. Photons were suddenly free to travel, and they have been traveling ever since. We detect that ancient light today as the cosmic microwave background radiation, a faint glow of microwave energy that fills the entire sky uniformly, the oldest light we can observe. After the fog cleared, the universe entered what astronomers call the cosmic dark ages. There were no stars yet, no galaxies, just vast clouds of neutral hydrogen and helium slowly settling under gravity. The universe was dark, cold, and featureless, at least at large scales. This period lasted until gravity had concentrated enough matter in the densest regions to trigger the ignition of the first stars. The first stars are thought to have been radically different from stars like our Sunday. They formed from primordial gas containing only hydrogen and helium, with none of the heavier elements that form in stellar interiors and get dispersed by supernova explosions. Without these heavier elements to radiate heat efficiently, the first collapsing gas clouds could not fragment the way modern ones do. Instead, they likely formed single, enormously massive objects, stars potentially hundreds of times more massive than the Sunday. These objects burned hot, fast, and bright, and died in violent explosions that seeded the surrounding gas with the first heavy elements. Gradually, over tens and hundreds of millions of years, these early stellar explosions and the continued collapse of gas under gravity assembled the first recognizable galaxies. That is the standard story. What Webb is seeing challenges the timeline of that story in a fundamental way. The galaxies it is finding are not just present at 300 million years after the Big Bang. They are present and already substantial. Some appear to have stellar masses comparable to the Milky Way at a time when the Milky Way should not yet have come anywhere close to existing. Let us take a step back and think about the mechanics of what the telescope is actually doing. When you point a telescope toward a patch of sky and observe a distant galaxy, you are not seeing that galaxy as it is now. You are seeing it as it was when the light you are detecting was emitted. Because light travels at a finite speed, roughly 300,000 kilometers per second, and because the universe is so vast, by the time ancient light reaches our detectors, enormous amounts of time have passed since it was emitted. Looking at a galaxy 12 billion light-years away means you are seeing it as it existed 12 billion years ago. This is one of the most remarkable features of observational astronomy. The sky is not a snapshot of the universe as it is today. It is a layered record of the universe at different moments in its history. The farther away you look, the further back in time you are looking. Webb exploits this to its maximum extent, peering so deep into space that it is effectively looking at the universe when it was only a small fraction of its current age. But the relationship between distance and observed age is complicated by expansion. The universe is not static. Space itself is expanding, which means that as light travels from a distant galaxy to our detectors, the space through which it travels is stretching. The light's wavelength stretches along with it, and the galaxy itself, while it was close to us when it emitted that light billions of years ago, has by now moved to a much greater distance as expansion continued. This is not intuitive, and it leads to some genuinely surprising conclusions. The observable universe is a sphere roughly 92 billion light-years in diameter. But the universe is only 13.8 billion years old. How can we see things 92 billion light-years away if light has only had 13.8 billion years to travel? The answer is expansion. Objects that were close to us when they emitted their light have since moved much farther away as space stretched. The light we are receiving from the most distant objects was emitted when those objects were much closer than they are today. The object has been carried to its current extreme distance by the subsequent expansion of space. Beyond the observable universe lies more universe, possibly vastly more. Some cosmological models suggest the universe is genuinely infinite. In that case, there is no edge, no boundary, and the Big Bang did not happen at a single point in space. It happened everywhere simultaneously. Every point in the current universe was once in contact with every other point. The expansion was not the spreading of matter through pre-existing space. It was the expansion of space itself, everywhere at once. The cosmic microwave background gives us a window onto this moment of expansion. Its temperature fluctuations, tiny variations of 1 part in 100,000, record the density variations in the early universe that would eventually grow, under gravity, into all the large-scale structure we observe today. Every cluster of galaxies, every cosmic filament, every vast empty void in the large-scale structure of the universe was seeded by those ancient fluctuations. Lambda CDM has been extraordinarily successful at explaining all of this. It predicts the pattern of fluctuations in the cosmic microwave background with remarkable precision. It explains the observed proportions of hydrogen and helium produced in the first few minutes after the Big Bang. It correctly predicts the distribution of galaxy clusters across cosmic time. So the stakes of what Webb is finding are high. This is not a model with known weaknesses looking for a replacement. This is one of the most successful frameworks in the history of science encountering observations it was not built to explain. Some researchers have gone further, suggesting that the apparent abundance of massive early galaxies might hint at physics that goes beyond simple modifications to galaxy formation theory. A small but scientifically serious group of cosmologists has raised the question of whether the Big Bang itself, as we currently conceive it, is the complete picture. Nobel Prize-winning physicist James Peebles, one of the architects of modern cosmology, has spoken cautiously but openly about the need to take anomalies seriously. He has noted that the history of science is full of cases where trusted models encountered observations they could not explain, and where those observations eventually forced genuine revisions. He is not claiming the Big Bang did not happen, but he and others have raised the legitimate scientific question of whether our current account of the universe's earliest history is missing important elements. Some alternative frameworks propose that the universe underwent a period of rapid inflation, during which space expanded exponentially fast in a fraction of a second after the Big Bang. Inflation is already part of the Standard Model, invoked to explain why the cosmic microwave background looks so uniform across the sky, despite the fact that, under a simple Big Bang model, regions on opposite sides of the sky should never have been in causal contact with each other. Inflation essentially proposes that all of these regions were once in contact, before being stretched apart by that rapid early expansion. Some theorists are now asking whether inflation itself might have left behind richer structures in the early universe than standard models predict. If the inflationary period was turbulent, or had a more complex structure, it might have seeded density fluctuations that were larger and more varied than simple inflation models produce, potentially explaining the early formation of massive structures. Others have turned to modified theories of gravity. General relativity is our best description of gravity at large scales, and it forms the foundation of Lambda CDM. But general relativity has never been tested in the extreme conditions of the very early universe. Some theorists have explored whether modifications to gravitational behavior at early times might have allowed matter to collapse and form structures more quickly than standard theory permits. There is also a more radical possibility that a small number of researchers have floated, not as a mainstream claim, but as a genuine scientific question worth examining. What if the universe has been through cycles? What if what we call the Big Bang was not the true beginning of everything, but rather a transition from a previous state of the cosmos? Cyclical or bouncing cosmologies have a long history in theoretical physics. Some versions propose that the universe contracts and then rebounds in a recurring cycle. Others suggest that our observable universe was spawned by a quantum fluctuation in a pre-existing state. None of these alternatives currently has the observational support that Lambda CDM does, but the anomalies Webb is revealing are making some physicists take them more seriously. It is worth being precise about what the evidence actually shows and what it does not yet show. What it shows is that there are objects in the early universe that appear, based on current observations, to be more massive, more luminous, and more structurally developed than Lambda CDM predicts they should be. Some of these detections have been confirmed spectroscopically. The galaxy counts in the early universe appear to exceed predictions in certain mass ranges. What it does not yet conclusively show is that Lambda CDM is wrong. The observations might be explained by modifications to the model that preserve its core structure. They might reflect incomplete understanding of star formation efficiency in the early universe. They might be partially explained by observational biases in how Webb detects and characterizes these objects. What scientists can say with confidence is that the data is not behaving the way the model predicted, and that this discrepancy deserves serious attention. Let us spend some time on the specific observational technique that makes these discoveries possible, because it is genuinely remarkable. The James Webb Space Telescope was launched on the 25th of December, 2021, folded inside an Ariane 5 rocket. It traveled about 1.5 million kilometers from Earth to a gravitationally stable location called the second Lagrange point, where the gravitational pulls of the Earth and Sun balance each other in a way that allows the telescope to orbit the Sun in lockstep with the Earth without consuming large amounts of fuel to maintain its position. Webb's sunshield, a 5-layer membrane the size of a tennis court, keeps the telescope's optics and detectors at temperatures around -233 degrees Celsius. This extreme cold is necessary for infrared observations. Infrared light is essentially heat radiation, and any warmth in the telescope's own structure would drown out the faint infrared signals from distant galaxies. The telescope uses 4 scientific instruments. The near-infrared camera, known as NIRCam, is the primary imaging instrument, and the one responsible for most of the deep-field images that have generated such excitement. The near-infrared spectrograph, or NIRSpec, can simultaneously take spectra of up to 200 objects at once, a capability that has dramatically accelerated follow-up confirmation of photometric detections. The mid-infrared instrument, MIRI, extends the telescope's wavelength coverage to longer infrared wavelengths, allowing observation of cooler objects and dust-obscured galaxies. And the near-infrared imager and slitless spectrograph, NIRIS, provides additional spectroscopic capabilities particularly useful for characterizing star-forming regions. Together, these instruments give Webb a remarkably comprehensive view of the infrared universe. The deep-field images that have revealed these anomalous early galaxies are produced by observing a relatively small patch of sky for extended periods. Each patch contains thousands of objects at varying distances. By carefully analyzing the brightness of each object across multiple wavelength bands, astronomers can estimate its redshift, and therefore its distance. This photometric redshift technique is then followed up with spectroscopy for the most significant objects. What makes Webb's deep field so powerful is not just the telescope's raw sensitivity, but its spatial resolution. Previous infrared observatories saw the early universe as a blur. Webb sees it in detail. Individual star-forming regions within early galaxies can be resolved. The shapes and structures of distant objects can be characterized. This resolving power is what allows astronomers to say not just that an early object exists, but that it looks like a mature, structured galaxy. The JADES program, the JWST, Advanced Deep Extragalactic Survey, is one of the major ongoing surveys producing these detections. It has devoted more than 750 hours of Webb's observing time to a single region of sky previously observed by Hubble, building up extraordinarily deep images in multiple wavelength bands. The discoveries emerging from JADES have produced some of the most significant galaxy candidates detected to date. The CEERS program, the Cosmic Evolution Early Release Science Survey, has also contributed major detections. It was CEERS data that produced some of the first announcements of extremely massive early galaxy candidates that generated headlines around the world when Webb's early results were released. What both programs continue to find is a consistent excess of bright, massive objects in the early universe compared to what Lambda CDM simulations predict. Theorists have not been standing still in the face of these results. One of the most actively explored explanations involves what happens when extremely massive early stars explode. The first generation of stars, the so-called population 3 stars formed from pure primordial hydrogen and helium, are thought to have been extraordinarily massive. When such stars end their lives in supernova explosions, the energy released can compress surrounding gas and trigger new rounds of star formation far more rapidly than the quiet, gradual process that builds most present-day galaxies. Some models propose that early bursts of intense star formation, driven by the feedback from these massive first stars, could have produced temporarily very bright objects that then faded as the star formation activity ended. Under this interpretation, what Webb is seeing as very luminous early galaxies might not be as genuinely massive as they appear. If a galaxy is undergoing a brief but intense burst of star formation, it will be temporarily much brighter than a galaxy of the same stellar mass that is forming stars at a more gradual rate. If Webb is catching many early galaxies during such bursts, the apparent abundance of massive early objects could be partly an observational selection effect rather than a true excess of stellar mass. This explanation has some appeal because it requires no modification to the fundamental physics of Lambda CDM. It simply requires that the early universe went through a phase of more intense, episodic star formation than models had previously assumed. But not all researchers find this explanation sufficient. The most extreme objects that Webb has detected appear too bright, even for this kind of burst-driven scenario. Some candidates, if confirmed at their photometric redshifts, would have stellar masses that simply cannot be produced by star formation bursts of any plausible intensity within the time available. A second theoretical line of investigation involves the role of active galactic nuclei, the supermassive black holes at the centers of galaxies that can become extraordinarily luminous when they are actively consuming material. An active galactic nucleus at high redshift can dramatically increase the apparent brightness of its host galaxy, potentially making the galaxy look more massive than it actually is. Some of Webb's most extreme early galaxy detections may contain embedded active galactic nuclei that are contributing significantly to their observed luminosity. Indeed, some follow-up observations have found signatures consistent with active galactic nuclei in a fraction of the most extreme early galaxy candidates. But active galactic nuclei cannot explain all of the detections, particularly those where the light distribution shows clear evidence of extended stellar emission rather than the compact, point-like appearance characteristic of a dominant central black hole. A third theoretical consideration involves the early formation of dust. Dust, composed of tiny grains of silicon, carbon, and other materials produced in stellar explosions, absorbs and re-radiates light in ways that can complicate the interpretation of galaxy observations. If early galaxies contained more dust than standard models predict, their intrinsic luminosity might be higher than observations suggest, because some of their light would be hidden by dust absorption. Alternatively, if galaxies appear bright in the infrared, some of that brightness might be coming from dust emission rather than direct stellar emission, changing the interpretation of the object's mass and age. The relationship between dust production and galaxy mass in the early universe is poorly understood, and Webb's observations of dust properties in early galaxies are actively contributing to our understanding of this relationship. Beyond the specific mystery of early galaxy masses, Webb's observations are generating broader questions about the epoch of reionization. After the cosmic dark ages, when the first stars and galaxies formed, the ultraviolet radiation they produced began to strip electrons from the neutral hydrogen atoms that filled intergalactic space. This process, called reionization, transformed the state of the universe from one filled with neutral gas to one where the intergalactic medium was predominantly ionized. Reionization is thought to have ended about 1 billion years after the Big Bang, but exactly when it started, how quickly it proceeded, and what sources drove it remain active areas of research. Webb is providing detailed views of the epoch of reionization for the first time. It can observe individual galaxies during this period, characterize their ultraviolet emission, and begin to build up a census of which types of galaxies were most important in driving the reionization of the universe. Early results suggest that the process may have been more patchy and complex than simple models predicted, with some regions of the universe reionizing earlier than others. This patchiness has implications for interpreting all of Webb's observations of early galaxies, because the opacity of the intergalactic medium to certain wavelengths of light changes as reionization proceeds, affecting which signals can be detected from galaxies at different distances. There is also an ongoing investigation into the first stars themselves. Population 3 stars have never been directly observed. They died billions of years ago, and any individual star would be too faint to detect directly even with Webb. But their chemical signatures should be imprinted in the composition of the galaxies that formed from the material they expelled. Webb's spectroscopic capabilities are sensitive enough to detect the chemical fingerprints of early generations of stars in some of the most distant galaxies, providing indirect evidence about the nature of the universe's first stellar populations. Some early results have suggested the presence of unusually high helium abundances and unusual ratios of nitrogen and other elements in certain early galaxy spectra, potentially consistent with the enrichment patterns expected from very massive first-generation stars. These are tantalizing but preliminary findings that will require additional observations and careful analysis to interpret. The broader picture that is emerging from Webb's first few years of operation is one of a universe that followed a somewhat different trajectory in its earliest phases than our best models predicted. The discrepancies are not so large that they require abandoning the entire Lambda CDM framework. But they are persistent and increasingly well documented, and they are driving a genuine rethinking of the details of how the first structures in the universe assembled themselves. This is precisely how science is supposed to work. A model that fits all known data gets tested against new observations. When those new observations reveal discrepancies, scientists work to understand whether the discrepancies reflect flaws in the model, limitations of the observations, or gaps in our understanding of specific physical processes. Sometimes the resolution requires only small adjustments to existing theory. Sometimes it requires more fundamental revision. The history of cosmology contains examples of both. The discovery that the expansion of the universe was accelerating, announced in 1998 based on observations of distant supernovae, required the addition of dark energy to the Standard Model, a profound modification that changed our picture of the universe's ultimate fate. The solution did not require abandoning general relativity or discarding everything previously known. But it did require acknowledging that our model of the universe had been missing one of its most important ingredients. It is not yet clear whether the early galaxy anomalies Webb is finding require a comparably significant revision. They might be explained by a better understanding of the astrophysics of early galaxy formation within the existing Lambda CDM framework. They might require modifications to the properties of dark matter. They might point toward a different inflationary scenario in the earliest moments of cosmic history. Or they might, in more speculative, but not dismissible territory, suggest that our picture of what happened before the conventional Big Bang is incomplete. What is clear is that the universe continues to surprise us. For most of human history, the sky was a mystery in its entirety. The nature of stars, the distances to the nearest ones, the existence of other galaxies beyond our own, these were all unknown within living memory, or within the last few generations. The realization that the universe had a beginning at all, that it had a history that could be traced back through observation, is one of the most profound developments in the history of human thought. Webb represents the most advanced tool humanity has ever built for continuing that investigation. In its first years of operation, it has already transformed our observational access to the early universe. The early galaxy problem it has uncovered is only one of many active areas of investigation, but it is perhaps the one that most directly challenges the foundations of our current cosmological model. Researchers are not sitting on their hands. Multiple teams are conducting follow-up spectroscopic observations of the most extreme early galaxy candidates. New theoretical simulations are being run that attempt to reproduce Webb's observations by adjusting the assumptions about early star formation efficiency, dust production, and feedback from active galactic nuclei. Proposals for even deeper survey programs are being developed. The Roman Space Telescope, NASA's next major infrared observatory currently in development, will eventually survey areas of sky hundreds of times larger than Webb's deep fields, providing the statistical samples needed to firmly establish whether the excess of early massive galaxies is a real, ubiquitous feature of the cosmos or a statistical fluctuation in the small area that Webb has observed so far. Ground-based observatories with extremely large mirrors, including the extremely large telescope being built in Chile and the 30-meter telescope planned for Hawaii, will provide complementary spectroscopic capabilities to confirm and characterize the objects Webb continues to discover. The next decade will see an enormous increase in both the quantity and quality of data bearing on these questions. The early galaxy problem that Webb has opened up is not going to remain unanswered for long. Whether the answer turns out to require modest adjustments to known physics, fundamental changes to our model of early cosmic history, or something genuinely unexpected, the investigation is already producing some of the most scientifically important observations in the history of astronomy. The universe began, evolved, and eventually produced beings capable of looking back at it and trying to understand how it works. That project is ongoing, and the James Webb Space Telescope has taken it to a new level entirely. What it is finding at the edges of the observable universe is a challenge, and challenges in science are not causes for alarm. They are the signal that deeper understanding is within reach. We do not yet know whether the early galaxies Webb is seeing will require a fundamental revision of the Lambda CDM model or a more limited adjustment to the physics of early galaxy formation. We do not yet know whether population 3 stars played a larger role in early structure formation than our models assumed, or whether the properties of dark matter in the early universe differed from what standard theory predicts. We do not know whether the epoch of reionization was driven primarily by the same types of galaxies that Webb is detecting, or by a population of objects that remains to be discovered. What we do know is that the universe's early history is stranger and richer than it appeared before Webb began returning data. The standard model of cosmology is being stress tested in a way it has never been before. And the results of that stress test, whatever they ultimately reveal, will reshape our understanding of how everything around us came to be. To appreciate the magnitude of what Webb is confronting, it is worth spending more time on the specific properties of the strange objects it is detecting, because the details are genuinely extraordinary, and the more you understand them, the more clearly you see why astronomers are so unsettled. Consider the galaxy catalog published by astronomer Haojing Yan and collaborators. Of the 87 candidate galaxies they identified in the early universe, many appear to have stellar masses in the range of tens of billions of times the mass of the Sunday. The Milky Way itself, our home galaxy after roughly 13 billion years of evolution, has a stellar mass of somewhere between 50 billion and 80 billion solar masses. Some of Webb's earliest detections are approaching that mass at a time when the universe was only about 2 to 3% of its current age. To form that much stellar mass in so little time requires an extraordinary rate of star formation. Modern galaxies form stars at rates measured in solar masses per year. The Milky Way currently forms roughly 1 to 2 stars per year, averaged across the entire galaxy. Some actively star-forming galaxies, called starburst galaxies, form hundreds of solar masses of stars per year. But they do so for relatively short periods before exhausting their gas supply or dispersing it through supernova feedback. To build the stellar masses Webb is observing in the time available, the early galaxy candidates would have needed to sustain star formation rates of hundreds or even thousands of solar masses per year for extended periods, essentially without interruption. Under current theory, such sustained high rates are extremely difficult to achieve because the feedback from massive stars, the radiation pressure, stellar winds, and eventually supernova explosions tends to disrupt the surrounding gas and suppress further star formation. The fact that some of these early galaxies appear to have already exhausted their gas supply, converting essentially all of it into stars, suggests that this feedback was either delayed or somehow less effective in the early universe. This is a specific, testable prediction that theorists are now working to model. One possibility involves the higher density of gas in the early universe. The universe was smaller and denser in its youth, which means that the gas in early galaxies may have been more tightly compressed. Denser gas is harder to disrupt with stellar feedback because the gas can recollapse more quickly after being blown outward. In this scenario, stellar feedback in early galaxies was less effective at suppressing star formation precisely because the environment was so much denser than in the present-day universe. This could have allowed early galaxies to sustain much higher star formation rates for longer periods. Another consideration involves the metallicity of the gas. Heavy elements produced in stellar interiors and dispersed by supernovae play an important role in the cooling of gas clouds. When gas can cool efficiently, it fragments into smaller clumps that collapse individually to form stars of moderate mass. Primordial gas, containing only hydrogen and helium, cools less efficiently and tends to form fewer, more massive stars. This difference in the initial mass function of stars, the distribution of stellar masses formed in a given star formation event, would change the energetics of the star-forming region and might allow for different patterns of feedback in gas consumption. The chemical composition of the objects Webb is detecting is therefore not just scientifically interesting in an abstract sense. It is directly relevant to understanding whether the physical conditions in early galaxies could have sustained the extreme rates of star formation apparently required to produce the observed stellar masses. Webb's spectroscopic instruments are capable of detecting the emission lines of specific elements in these distant galaxies. Oxygen, hydrogen, nitrogen, and carbon all produce characteristic spectral lines that can be identified even at the enormous redshifts of these early objects. The ratios of these emission lines encode information about the temperature, density, and metallicity of the gas in the galaxy. Early results from several of these distant objects have shown unusual chemical signatures, sometimes with higher nitrogen to oxygen ratios than expected, or unusual ionization conditions suggesting exposure to very hard ultraviolet radiation. Some of these unusual chemical signatures are consistent with what you might expect from a population of extremely massive stars, stars many hundreds of times more massive than the Sun, of the kind that are thought to have formed in the very earliest phase of cosmic history. Other signatures might indicate the presence of an active galactic nucleus, the extremely luminous core powered by a growing supermassive black hole. Distinguishing between these two possibilities requires careful spectral analysis and often additional multi-wavelength observations. The question of how the first supermassive black holes formed is itself a profound mystery that Webb is helping to address. In the present-day universe, the most massive galaxies have supermassive black holes at their centers, with masses proportional to the mass of the host galaxy's central stellar bulge. This tight relationship between black hole mass and galaxy properties suggests that the two evolved together, each influencing the growth of the other through a process astronomers call co-evolution. But in the early universe, Webb is finding evidence for supermassive black holes that already have masses of billions of solar masses when the universe was less than 1 billion years old. Growing a black hole to that mass in so little time is extraordinarily challenging. The standard pathway for black hole growth involves accretion, the consumption of surrounding gas and stars, but there is a physical limit to how quickly a black hole can consume material. When the material falls in too fast, the radiation pressure from the infalling gas can push away the surrounding matter and shut off further accretion. This limit is called the Eddington limit. To reach the observed masses of early supermassive black holes by the Eddington limit alone would require starting with seed black holes of at least 1,000 to 1 million solar masses within the first few 100 million years of the universe's history. Standard stellar evolution produces black holes of at most a few hundred solar masses from the collapse of massive stars. Bridging the gap between stellar mass black holes and the seeds required for early supermassive black holes is an unsolved problem that goes by the name of the black hole seed problem. Webb is providing the observational data that may eventually point toward the solution. By detecting active galactic nuclei at the earliest epochs and measuring their properties, astronomers can constrain the masses and growth rates of the earliest supermassive black holes. If black holes with masses of 100,000 to 1 million solar masses existed when the universe was only a few 100 million years old, that would strongly suggest a formation pathway that does not involve sequential accumulation from stellar mass seeds, but rather the direct collapse of massive gas clouds in the early universe. The direct collapse black hole scenario is one of the leading theoretical proposals for producing supermassive black hole seeds. Under this idea, a rare but possible set of conditions in the early universe, a massive cloud of primordial gas in a region of space with unusually high ultraviolet background radiation, could lead to the collapse of the entire gas cloud as a single object rather than fragmenting into many individual stars. The resulting object, called a direct collapse black hole, would have a mass of 100,000 solar masses or more, providing the head start needed to grow a supermassive black hole by the times Webb is observing. Evidence for such objects has been circumstantially present for some years, but Webb is providing much more detailed observations of candidate direct collapse, black holes, and the extreme environments in which they form. To fully appreciate why the universe's early history matters so much, consider what it means for everything that came later, including us. Every heavy element in the universe beyond hydrogen and helium was produced inside stars. The carbon in organic molecules, the oxygen we breathe, the iron in our blood, the silicon in rocks, all of it was forged in the interiors of stars and dispersed into space when those stars died. The first generation of stars, formed from pure primordial gas, did not have any of these elements. They lived, burned through their fuel, and exploded, seeding the surrounding gas with the first batch of heavy elements. The second generation of stars formed from gas enriched by those explosions, and so on through many generations. The timeline of this chemical enrichment, the sequence by which the universe went from a pure hydrogen and helium composition to one containing all the elements needed for rocky planets and biology, depends critically on when the first stars formed and how they evolved. If the first galaxies formed more rapidly than current models predict, then the chemical enrichment of the early universe also proceeded more rapidly, which could have implications for when planets like Earth could first have formed and when life could have first become possible anywhere in the cosmos. Some researchers have speculated, cautiously and with appropriate acknowledgement of the vast uncertainties involved, that if the universe was chemically enriched earlier than expected, then the conditions for rocky planet formation and potentially for biology may have been present earlier than standard theory suggests. This is highly speculative, and the path from early chemical enrichment to habitable planets involves an enormous number of additional steps that we do not yet understand well. But it illustrates how the seemingly arcane question of when the first galaxies formed connects, in principle, to some of the deepest questions about our place in the cosmos. The deep field images Webb has been producing are themselves stunning objects of scientific and human significance. In a patch of sky small enough to be covered by a grain of sand held at arm's length, thousands of galaxies are visible, each containing hundreds of billions of stars, each at a different distance, and therefore, a different moment in cosmic history. The nearest are perhaps a few 100 million light-years away. The most distant are over 13 billion light-years away. In a single image, Webb provides a cross-section of cosmic history spanning most of the universe's existence. The precision required to produce these images is staggering. Webb must maintain its orientation with extreme stability, unable to move by more than the equivalent of 1 arcsecond in 24 hours, while building up exposures that may last for dozens of hours. Its optics must be aligned to nanometer precision. Its detectors must operate at temperatures so cold that they can record individual photons from galaxies that emitted their light before the Earth existed. The engineering achievement of the Webb telescope is inseparable from the scientific achievement of what it is revealing. It represents the accumulated expertise of thousands of engineers, scientists, and project managers working over more than 2 decades. Its launch and deployment, involving the unfolding of a golf course-sized sunshield in the vacuum of space, executed without any possibility of human intervention, was one of the most complex mechanical procedures ever performed. The fact that it worked, that the telescope reached its destination, deployed correctly, cooled to operating temperature, and began producing scientifically groundbreaking observations, is an extraordinary testament to human ingenuity and persistence. But the scientific questions it is now raising are, if anything, even more extraordinary than the engineering feat itself. Because what Webb is showing us is that the universe in its youth was doing things we did not expect, building structures faster than our best theories said was possible, assembling matter into organized forms with an efficiency that challenges our understanding of the physical processes involved. This is not a crisis for cosmology. It is, in the most literal sense, progress. Science advances when observations push beyond the boundaries of existing understanding. The current anomalies in Webb's early universe observations are not destroying our knowledge. They are extending the frontier of what we need to understand. The Lambda CDM model will survive in some form. Its successes are too numerous and too precise to be entirely wrong. The cosmic microwave background observations, the large-scale structure measurements, the predictions of element abundances from Big Bang nucleosynthesis, all of these continue to confirm the broad outlines of our cosmological picture. What is being revealed is that the details of early galaxy formation within that broad picture require revision. Whether that revision turns out to be modest or profound, it is happening in real time. The data from Webb is publicly released and available to researchers around the world. The papers examining these early galaxy detections are being written, reviewed, and published at a rapid pace. Theoretical models are being updated and challenged. Observational follow-up is ongoing. The scientific community is responding to these anomalies exactly as it should, with rigorous examination, healthy skepticism, and energetic investigation. The discoveries are also generating wider cultural resonance. The images Webb has produced have been viewed by hundreds of millions of people around the world. The question of what the universe was like in its earliest moments, when the first light in the cosmos was just beginning to shine, is not merely a technical puzzle for specialists. It is one of the most fundamental questions human beings have ever asked. Where did everything come from? How did the structured, complex, chemically rich universe we inhabit emerge from the hot, featureless fireball of the Big Bang? What came before, if anything? Are the structures we see the inevitable result of physics playing out in a universe with particular initial conditions? Or could other universes with different properties exist somewhere beyond our horizon? Webb is not going to answer all of these questions, but it is providing the most detailed observational window onto the early universe that humanity has ever had. And what it is showing us is that the universe's early history was more complex and more interesting than we imagined. That is not a failure of our models. It is an invitation to understand more deeply. The anomalous early galaxies that Webb is detecting, these objects too bright, too massive, and too structured for their place in the standard timeline, are not just puzzles to be solved and moved on from. They are windows onto physics and processes we do not yet fully understand. They are data points that will shape the development of cosmological theory for decades to come. And they are reminders that the universe, for all the remarkable progress of modern science in understanding it, remains a place full of genuine surprises. In the coming years, as Webb continues to observe, and as the community of astronomers continues to analyze its data, the picture of the early universe will sharpen. The most extreme anomalies will either be confirmed or explained away. The genuine discrepancies with standard theory will be quantified more precisely. And the theoretical models will evolve in response, incorporating new insights about star formation, black hole growth, dark matter properties, and the physics of the very early universe. The story of what Webb is finding is not finished. In many ways, it is just beginning. The telescope has years of planned observations ahead of it, and the scientific community is only beginning to work through the implications of what it has already detected. The early galaxies Webb has found at the edge of the observable universe are not going to stop demanding explanation. If anything, as more observations accumulate and the statistical significance of the anomalies grows, the pressure on theorists to account for them will only increase. What comes next in this story will depend on observations, calculations, and insights that have not yet been made, but the direction is clear. We are learning that the universe in its earliest phase was building structure faster, more efficiently, and in ways more complex than our current understanding predicted. Accounting for that difference is the central challenge now facing observational and theoretical cosmology. The tools to meet that challenge are being deployed. The scientists working on it are among the most capable in the world. And the universe, as it always has, will eventually give up its secrets, revealing itself more fully to the curious beings who have dedicated themselves to understanding it. Let us step back even further and consider the observational history that led to the construction of Lambda CDM in the first place. Because understanding why scientists trust it so much also illuminates why the anomalies Webb is finding carry such weight. The story begins in 1917, when Albert Einstein first applied his newly completed theory of general relativity to the universe as a whole. General relativity describes gravity not as a force, in Newton's sense, but as the curvature of space-time caused by the presence of mass and energy. A massive object like the Sun warps the fabric of space-time around it, and other objects moving through that warped space-time follow curved paths that we perceive as gravitational attraction. When Einstein tried to apply this to the entire cosmos, he ran into an immediate problem. His equations predicted that the universe could not be static. It should either be expanding or contracting. Einstein, like nearly everyone of his era, believed the universe was eternal and unchanging. So he introduced a term into his equations, the cosmological constant, specifically to counteract the predicted expansion or contraction and produce a static solution. He later described this as the greatest blunder of his scientific career, though as we will see, the story has an interesting twist. In 1929, Edwin Hubble published the observations that changed everything. Working at the Mount Wilson Observatory in California with the world's most powerful telescope at the time, Hubble had been systematically measuring the distances to other galaxies, which most scientists of that era did not even know were separate galaxies rather than clouds of gas within the Milky Way. By identifying a type of variable star called a Cepheid, whose intrinsic luminosity is directly related to its pulsation period, Hubble was able to calculate the true distances to nearby galaxies. He found that the galaxies with the highest recession velocities were also the most distant. The relationship between distance and recession velocity was remarkably linear, a result now known as Hubble's law. The interpretation was straightforward, but astounding. The universe was expanding. All galaxies were moving away from one another, not because they were flying through space, but because the space between them was stretching. And if you ran this expansion backward in time, everything converged on a single point of origin. Hubble's observation instantly removed the need for Einstein's cosmological constant and provided the observational foundation for what would become the Big Bang model. The next major confirmation came from an unexpected direction. In 1948, physicists Ralph Alpher and Robert Herman, working with George Gamow, predicted that if the early universe had been hot and dense, the cooling fireball should have left behind a pervasive background of thermal radiation filling the entire sky. They calculated that this radiation, now cooled by billions of years of cosmic expansion, should be detectable as microwave radiation with a temperature of a few degrees above absolute zero. In 1964, radio astronomers Arno Penzias and Robert Wilson, working at Bell Telephone Laboratories in New Jersey, were plagued by a persistent noise in their radio antenna that they could not explain. After exhausting all possible instrumental explanations, including removing pigeon nests from the antenna, they eventually recognized that the noise was real. It was coming from every direction in the sky with equal intensity. It was the cosmic microwave background, the echo of the Big Bang that Alpher and Herman had predicted 16 years earlier. Penzias and Wilson were awarded the Nobel Prize in Physics in 1978 for this discovery. The cosmic microwave background is not just a uniform glow. It has tiny temperature variations of about 1 part in 100,000 across the sky. These fluctuations were first mapped in detail by the COBE satellite in the early 1990s, work that earned the Nobel Prize for John Mather and George Smoot in 2006. The WMAP satellite later produced much more detailed maps, and the Planck satellite, which operated from 2009 to 2013, produced the highest precision map of the cosmic microwave background yet achieved. The Planck data was analyzed to extract a wealth of cosmological information. The pattern of temperature fluctuations across the sky, described mathematically in terms of their angular power spectrum, encodes information about the geometry of the universe, the relative amounts of ordinary matter, and dark energy, the age of the universe, and the overall curvature of space. When cosmologists fit the Lambda CDM model to the Planck data, they find extraordinary agreement. The model, with 6 free parameters, fits the observations across a huge range of angular scales with a precision that has no precedent in the history of science. This is why abandoning Lambda CDM is not something any serious cosmologist proposes lightly. It is not a rough sketch that might easily be wrong. It is a precisely quantified framework that has been tested against the most detailed cosmological observations ever made and found to be extraordinarily accurate. And yet, the expansion rate of the universe provides an independent measure of cosmological parameters. The expansion rate today is quantified by the Hubble constant, which Hubble originally measured, with the technology of his era, at around 500 kilometers per second per megaparsec, a unit meaning that for every megaparsec, roughly 3.3 million light-years of distance between two objects, the recession velocity between them increases by 500 kilometers per second. Hubble's original measurement was much too high, a consequence of his distance scale being systematically off, but subsequent generations of measurements have refined it. In recent years, a serious discrepancy has emerged between different methods of measuring the Hubble constant. Measurements based on the cosmic microwave background and Lambda CDM theory give a value of about 67 kilometers per second per megaparsec. Direct measurements using Cepheid variable stars and Type Ia supernovae, the techniques refined over decades by teams including those led by Adam Rees, give a value of about 73 kilometers per second per megaparsec. This difference of about 10%, known as the Hubble tension, is far too large to be explained by measurement errors, given the precision of the observations. Either one or both methods has some systematic error that has not been identified. Or the Lambda CDM model is missing some physics. The Hubble tension is separate from the early galaxy problem Webb is revealing, but they may be related. Both anomalies point toward a potential incompleteness in our understanding of cosmic evolution, though the connection between them is not yet clear. Some theorists have proposed modifications to dark energy, allowing its energy density to vary over time rather than remaining constant, as a possible explanation for the Hubble tension. Others have proposed modifications to early dark energy, a component of energy that was significant in the early universe but has since diluted away. These modifications sometimes improve the agreement with one set of observations, but worsen it with another, suggesting that no simple addition to the standard model yet resolves all the tensions simultaneously. The situation is one of productive uncertainty. There is enough evidence of discrepancy to motivate serious theoretical work, but not enough clarity about the nature of the discrepancy to point unambiguously toward a specific solution. This is actually a familiar situation in the history of physics. In the late 19th century, the dominant theoretical framework for understanding heat and light predicted that a hot object should radiate an infinite amount of energy at short wavelengths, a nonsensical result known as the ultraviolet catastrophe. The resolution came through an entirely new framework, quantum mechanics, which introduced the idea that energy is exchanged in discrete packets rather than continuously. The ultraviolet catastrophe was not a signal that thermodynamics was entirely wrong. It was a signal that thermodynamics was missing a crucial piece of physics. The resolution to that missing piece changed our understanding of the physical world more profoundly than anyone anticipated. Whether the current anomalies in cosmology will require a similarly revolutionary revision, or whether they will be resolved through more modest extensions of existing theory, is genuinely unknown. The honest answer is that we do not know yet. What we can say is that the universe is providing us with new information through Webb that we did not have before. That information is creating productive challenges for our best models. And the scientific community is responding to those challenges with the tools, the curiosity, and the intellectual rigor that the questions demand. Webb is not just finding puzzling early galaxies. It is also transforming our understanding of galaxy evolution at all cosmic epochs, not just the earliest times. One of the surprising things about galaxy evolution is how dramatically galaxies change over cosmic time. The most common galaxies in the nearby universe are relatively passive, red, old systems that have essentially stopped forming new stars. But when you look at the universe at earlier times, these passive galaxies are much rarer. The universe a few billion years ago was dominated by intensely star-forming galaxies, blue and bright, actively building their stellar populations. Understanding how these star-forming galaxies of the past became the passive galaxies of today is one of the central problems in galaxy evolution research. The leading explanation involves feedback from supermassive black holes. When a galaxy's central black hole becomes sufficiently massive and is accreting material at a high rate, it can drive powerful jets and winds of gas that heat and expel the galaxy's star-forming material, shutting down further star formation and leaving the galaxy as a passive relic. This process, called quenching, is thought to be responsible for the transformation of active star-forming galaxies into passive red ones. Webb is providing unprecedented views of the quenching process in action. It is detecting massive, compact galaxies that appear to have already shut down their star formation at very early cosmic times, within the first few billion years of the universe's history. Some of these quenched early galaxies are surprisingly compact, smaller than the passive galaxies of the present-day universe with similar masses. This compactness is itself a puzzle, because subsequent galaxy evolution should involve mergers and acquisitions that add mass and size over time. How these compact early passive galaxies transformed into the extended passive galaxies of today is another active area of investigation that Webb is providing crucial data for. The diversity of galaxy morphologies that Webb is revealing at early cosmic times is itself one of the more striking results of its initial years. Before Webb, the highest redshift galaxies observable were little more than fuzzy blobs in the deepest Hubble images. Webb's superior resolution and sensitivity reveal that even very early galaxies have structure: spiral arms, bars, disk components, signs of ongoing mergers and interactions. The universe was not simply a collection of featureless, amorphous blobs in its early phases. It was already producing the diverse menagerie of galaxy types that we see more fully developed in the nearby universe. This structural complexity at early times is another surprise. Traditional models predicted that the earliest recognizable galaxies would be small, irregular, and devoid of the organized structures like spiral arms that require a settled, rotating disk. The appearance of such structures earlier than expected adds to the general picture that the early universe was building cosmic structures more rapidly and in more sophisticated ways than we assumed. The implications of all of this extend beyond the specific question of when galaxies formed and how massive they were. They touch on the fundamental nature of the dark matter that makes up most of the universe's mass. We cannot see dark matter directly. It does not emit, absorb, or reflect light of any kind. We infer its existence and properties from its gravitational effects on ordinary matter. The rotation curves of galaxies, the bending of light by galaxy clusters, the large-scale distribution of matter in the universe. All of these observations are consistent with the presence of dark matter in quantities several times larger than the total amount of ordinary matter. Cold dark matter, the CDM in Lambda CDM, refers specifically to dark matter particles that move slowly compared to the speed of light. In the early universe, when temperatures were high, even slow-moving particles could move fast enough to smooth out density fluctuations on small scales. As the universe cooled, these particles slowed further and became fully non-relativistic, allowing small-scale density fluctuations to grow. The smallest structures to form first under cold dark matter are very small, roughly the mass of Earth or less. These small dark matter halos then aggregate into larger ones in a process called hierarchical structure formation, building up from small to large over time. This hierarchical picture has been remarkably successful at explaining the large-scale structure of the universe. But it makes specific predictions about the number and properties of small dark matter halos, particularly the small satellite galaxies that should orbit inside larger host halos. Observations of the Milky Way and nearby galaxies reveal fewer small satellite galaxies than cold dark matter simulations predict, a problem known as the missing satellites problem. Several solutions have been proposed. Baryonic feedback, the heating and ejection of gas by stellar feedback and supernova explosions in small halos, could prevent small halos from forming visible galaxies even if the dark matter structure is present. Or the dark matter itself could have properties that suppress the formation of small structures. Warm dark matter particles, moving faster than cold dark matter in the early universe, would smooth out small-scale fluctuations and produce fewer small halos to begin with. Fuzzy dark matter, an extremely light particle behaving quantum mechanically on cosmological scales, would produce a minimum scale below which structure is suppressed. Webb's observations of early galaxies are potentially sensitive to these differences. The number density of small galaxies at high redshift, the abundance of the faintest early galaxy detections, and the statistical properties of the large-scale distribution of early galaxies all carry information about the nature of dark matter. As Webb accumulates more data and the analysis matures, these observations may begin to distinguish between different dark matter models in ways that previous observations could not. This is the remarkable thing about the current moment in astronomy. Webb is not just addressing a single question. Its observations touch simultaneously on galaxy formation theory, dark matter physics, black hole growth mechanisms, the physics of reionization, the chemical enrichment history of the universe, and the fundamental parameters of the cosmological model. It is, in a very real sense, providing a stress test of our entire understanding of how the universe evolved from its hot, featureless beginning to the complex, structured cosmos we inhabit today. Some of these stress tests are producing results that fit comfortably within existing theory. Others are producing the anomalies we have been discussing. And some are producing surprises of a different kind, not violations of existing theory, but unexpected phenomena that fall within the model's predictions while being nonetheless astonishing. One such phenomenon is the detection of molecular gas in extremely distant galaxies. Molecular hydrogen, carbon monoxide, and water vapor have been detected in galaxies at redshifts that correspond to the universe being only a few 100 million years old. The presence of molecules at such early times requires that some degree of chemical enrichment had already occurred. and that the conditions in these early galaxies were already favorable for the chemistry of the interstellar medium to proceed. These detections open a window onto the detailed physical conditions of early star-forming regions that was simply inaccessible before Webb. Another surprising result involves the detection of what appear to be mature stellar populations in very early galaxies. Some early galaxies appear to contain significant numbers of old stars, stars that must have formed even earlier than the galaxies themselves were detected. This points toward a complex, layered history of star formation in the early universe, with multiple generations of stars forming and dying within the first few 100 million years. The chemical signatures of these early stellar generations are imprinted in the composition of the gas and stars of the galaxies Webb is observing, providing a fossil record of the universe's earliest epochs. The scientific work required to fully extract the information contained in Webb's observations is enormous and will take many years. The raw data must be processed through sophisticated pipelines that correct for instrumental artifacts, calibrate the photometry and spectroscopy, and produce reliable source catalogs. Each source must then be analyzed individually and in statistical ensembles. The results must be compared with theoretical models and simulations. New theoretical work must be motivated by the observations and tested against them. This iterative process is the normal rhythm of observational science, but Webb is producing data at a pace and depth that is stretching the capacity of the community to keep up. There are more potentially interesting objects in Webb's deep fields than there are astronomers to analyze them. New analysis methods, including machine learning techniques that can automatically classify large numbers of objects and identify the most unusual ones for follow-up, are being developed and applied. The broader scientific community beyond professional astronomy is also engaged with these questions. Cosmologists, particle physicists, and theoretical physicists of all kinds are paying close attention to Webb's results because the anomalies it is finding potentially touch on physics well beyond galaxy formation. If the early universe truly did produce structures more rapidly than Lambda CDM predicts, the explanation might lie in physics at energy scales inaccessible to any particle accelerator. Physics from the first fractions of a second of cosmic history that left imprints in the distribution of matter and the properties of the structures that grew from it. The connection between early universe physics and the structures Webb is observing is mediated by the primordial power spectrum, the statistical distribution of density fluctuations left behind by inflation. Standard inflation produces a nearly scale-invariant power spectrum, meaning that density fluctuations of different sizes are present with roughly equal amplitude. But modifications to inflation, different field configurations, different energy scales, different coupling constants, all produce slightly different power spectra that leave slightly different imprints in the statistics of galaxies and their large-scale distribution. Webb's observations, combined with other cosmological measurements, are therefore providing constraints on the physics of inflation in a way that complements what can be learned from the cosmic microwave background alone. The combination of these different datasets, each sensitive to different aspects of early universe physics, is giving cosmologists an increasingly detailed picture of the conditions that prevailed in the universe's earliest moments. Whether this picture will ultimately require new physics beyond the standard models of both cosmology and particle physics, or whether the current anomalies will be resolved within the existing framework, is the central open question. The answer will depend on observations and analysis that are actively underway. What is certain is that we are living through a remarkable moment in the history of astronomy. For the first time, we have a tool capable of observing the universe in detail during its earliest epochs of galaxy formation. The data that tool is returning is challenging our expectations in ways that are both scientifically important and genuinely exciting. The early universe is speaking to us through the ancient light collected by Webb's mirrors. The message it is sending is that the story of cosmic origins is more complex, more surprising, and more interesting than the best minds of a generation had managed to work out before the telescope launched. Deciphering that message fully will take years of observation, analysis, and theoretical development. But the work is underway, and the universe, as always, has proven more generous with its surprises than with its answers. It is also worth exploring the technical history of how we came to understand what we mean when we say the universe had a beginning. Because that understanding was far from obvious and required decades of painstaking observational and theoretical work. When Hubble measured the recession velocities of distant galaxies in 1929, the immediate implication that the universe was expanding and that it must therefore have been smaller and denser in the past was clear to relativists like Georges Lemaitre, who had actually independently derived the expanding universe solution to Einstein's equations before Hubble's observations. Lemaitre called the original state of the universe a primeval atom, a dense, hot origin point from which the expansion began. But it was not until the 1940s and 50s that physicists began working out the detailed physics of what that hot, dense early state would have looked like and what observable consequences it would have left behind. The term Big Bang was actually coined by astronomer Fred Hoyle in 1949 as a dismissive label for a theory he opposed. Hoyle was a proponent of the steady-state model, which proposed that the universe had always existed in roughly its current form, with new matter continuously being created as the universe expanded to maintain a constant average density. The steady-state model had the philosophical appeal of not requiring a beginning, but it was ultimately ruled out by observations, most decisively by the discovery of the cosmic microwave background, which is naturally explained by the Big Bang model and has no sensible explanation in the steady-state framework. With the confirmation of the Big Bang, cosmology entered an era of rapid progress. The theory of Big Bang nucleosynthesis, developed by William Fowler, Fred Hoyle, and others in the 1950s and 60s, showed that the proportions of hydrogen, helium, and small amounts of lithium and deuterium produced in the first few minutes of the universe's existence could be calculated from the known physics of nuclear reactions. The predicted proportions, particularly the helium to hydrogen ratio of about 1 part helium to 3 parts hydrogen by mass, matched observations of the oldest stars and most pristine gas clouds with remarkable precision. This agreement between theory and observation was one of the strongest early confirmations of the Big Bang framework. The theory of inflation, first proposed by physicist Alan Guth in 1980, addressed several puzzling aspects of the Big Bang model that had not previously been explained. Why is the cosmic microwave background so uniform across the sky, even in regions that, under simple Big Bang expansion, could never have been in causal contact with each other? Why is the universe's geometry so close to perfectly flat, with no detectable large-scale curvature? Why are there no magnetic monopoles or other exotic relics from the very early universe that particle physics theories predicted should have been produced in abundance? Inflation answered all of these questions by proposing that the universe underwent a period of exponential expansion, driven by a form of energy called the inflaton field, in the first tiny fraction of a second after the Big Bang. During this inflationary period, the universe expanded by a factor of at least 10 to the power of 26 in a time interval of less than 10 to the power of negative 32 seconds. This enormous expansion stretched any initial curvature flat, diluted any pre-existing exotic particles to undetectable densities, and brought every point in the currently observable universe into causal contact before it was stretched apart. Inflation also provided a natural mechanism for generating the tiny density fluctuations that seeded the large-scale structure of the universe. Quantum mechanical fluctuations during the inflationary period were stretched to macroscopic scales by the rapid expansion, producing a nearly scale-invariant spectrum of density perturbations that matches the observed pattern in the cosmic microwave background with high precision. The detailed predictions of inflation have been tested with extraordinary precision by the Planck satellite and other experiments. The fact that inflation works as well as it does is one of the strongest arguments for accepting it as part of the standard cosmological model. But inflation is not a single theory. It is a framework within which many specific models can be constructed, with different shapes of the inflaton potential, different energy scales, and different predicted details of the primordial perturbation spectrum. Distinguishing between these specific models requires observations of increasing precision. One of the key signatures that would distinguish between inflationary models is the presence and amplitude of primordial gravitational waves, ripples in spacetime produced during inflation that leave a specific pattern of polarization in the cosmic microwave background. Detecting this signature, called B-mode polarization, is one of the goals of several ongoing and planned experimental programs. So far, no confirmed detection of primordial B-mode polarization has been made, which places constraints on the energy scale of inflation and rules out some of the simplest inflationary models. Future experiments with greater sensitivity may eventually detect this signal and provide direct evidence about the energy scale and mechanism of inflation. All of this background helps illustrate the layered structure of modern cosmology. The Big Bang framework provides the broad outline. Lambda CDM fills in the details of what the universe is made of and how it evolved. Inflation explains the initial conditions. And ongoing observational programs, including Webb, are testing every component of this framework against the universe itself. The early galaxy anomalies that Webb is finding are a challenge primarily to the CDM component of Lambda CDM, specifically to the models of how cold dark matter halos assemble and how galaxies form within them. But they also have implications for the inflationary component if they require an explanation involving a non-standard primordial power spectrum. And they have potential implications for the lambda component if the explanation involves modifications to how dark energy behaved in the early universe. This interconnectedness is both one of the most challenging and most fascinating aspects of modern cosmology. The universe does not divide itself neatly into separate questions. Every observation potentially bears on multiple components of the theoretical framework, and a change to one part has implications for others. This is why the anomalies Webb is revealing are treated with such seriousness despite their preliminary status. They may be pointing at something deeper than they initially appear. The question of whether the universe had a true beginning, or whether something existed before what we call the Big Bang, is one that science has struggled with for decades. The Big Bang, as described by general relativity, is technically a singularity, a point at which the equations break down and cease to make meaningful predictions. General relativity, our best theory of gravity in space-time at large scales, is not a complete theory because it does not incorporate quantum mechanics. At the extreme conditions of the very early universe, quantum effects must have been important, but we do not yet have a complete theory of quantum gravity to describe what happened at that moment. String theory and loop quantum gravity are among the leading candidates for theories of quantum gravity, but neither has yet made observational predictions that can be tested. Some versions of loop quantum cosmology suggest that the Big Bang was actually a big bounce, a moment when a previous contracting universe reached a maximum density and then rebounded into expansion. In these models, the universe has no true beginning but has been cycling through contracting and expanding phases for an indefinitely long time. Some versions of string theory likewise suggest a landscape of possible universes, with our observable cosmos being just one bubble in a vast multiverse, each region with potentially different physical constants and laws. These ideas remain highly speculative because they currently make no predictions that can be tested with available technology. But they represent the frontier of theoretical physics and cosmology, the attempt to push our understanding beyond the boundary that general relativity sets at the Big Bang singularity. What makes the current moment particularly interesting is that Webb's observations are beginning to probe conditions close enough to that boundary to potentially be sensitive to effects beyond standard inflation and Lambda CDM. Not the singularity itself, but the era close enough that any unusual physics from the very beginning might have left detectable traces in the distribution and properties of the first galaxies. If the first structures in the universe formed faster than Lambda CDM predicts, one possible explanation is that the initial power spectrum of density fluctuations, the seeds planted by inflation, was different from what standard inflation predicts. Specifically, if the power spectrum had more power on small scales, meaning stronger density fluctuations at small sizes, then small structures would have formed earlier and grown more quickly, potentially explaining the abundance of massive early galaxies. Such a modified power spectrum could reflect non-standard physics during inflation, potentially providing a rare observational window onto the otherwise inaccessible physics of the inflationary epoch. This is a genuinely exciting possibility. If Webb's anomalies ultimately require a non-standard inflationary power spectrum, they would be providing indirect evidence about the physics that governed the universe in its first tiny fraction of a second, an epoch so early and so energetically extreme that it will never be accessible through any particle accelerator we could build. The next few years will be critical in determining whether this or any other explanation for the anomalies is correct. follow-up spectroscopic confirmation of the most extreme early galaxy candidates, statistical analyses of the full population of high redshift objects in Webb's deep fields, comparisons with state-of-the-art cosmological simulations, and observations from complementary facilities will all contribute to narrowing down the possibilities. The telescopes that will follow Webb, including the Roman Space Telescope with its enormous field of view, and the ground-based extremely large telescopes with their superior spectroscopic capabilities, will collectively multiply the amount of data available about the early universe by orders of magnitude. Statistical analyses that are currently limited by sample size will eventually have enough objects to test theoretical predictions at a level of precision currently impossible. And the theoretical models that need to explain these observations will be developed and tested against an ever richer dataset. The combination of observational data and theoretical insight that defines the scientific method is working exactly as it should, pushed forward by a discovery machine as powerful and precise as the James Webb Space Telescope. What Webb has accomplished in its first years of operation is a remarkable expansion of our observational horizon. Not the physical horizon of the observable universe, which is set by the speed of light and the age of the cosmos, but the practical horizon of what we can actually see and measure. For the first time, we are not guessing at the properties of the earliest galaxies from indirect arguments or extrapolations from closer objects. We are observing them directly, in detail, across a range of wavelengths, and with enough resolution to see their structure. And what we are seeing is a universe that, in its youth, was more dynamic, more efficient, and more surprising than we had predicted. Objects too massive for their age. Chemical enrichment too rapid for standard timelines. Black holes too large for the seeds available to them. Galaxies too structured for their brief time in existence. Each of these surprises is a question mark written in ancient starlight. And answering those questions, working out why the early universe behaved the way it did, is the central project that Webb has opened up for this generation of astronomers and cosmologists. The answers will come. They always do, eventually, in the long story of science. Sometimes they arrive as corrections to the model, adjustments that preserve the fundamental framework while fixing a specific deficiency. Sometimes they arrive as genuine revolutions, new frameworks that supersede the old ones while incorporating their successful predictions. Which kind of answer is waiting at the end of this particular investigation? Nobody knows yet. What is certain is that the investigation is underway. The data is being collected, analyzed, and debated by some of the most capable scientists alive. The tools available to them are the most powerful ever built for this purpose. And the universe, as it always has, is yielding its secrets slowly, one photon at a time, to those patient and skilled enough to receive them. The story of the James Webb Space Telescope and what it is revealing about the early universe is, at its core, a story about the human capacity for curiosity and the extraordinary lengths to which that curiosity can drive us. We built a telescope the size of a tennis court, launched it 1.5 million kilometers into space, cooled it to within 40 degrees of absolute zero, and pointed it at the oldest light in the universe. We did all of this because we wanted to know where everything came from. The answer, so far, is that everything came from conditions stranger and more complex than we had imagined. That is not a disappointment. It is an invitation. The universe is more interesting than our best theories said it should be. And in the history of science, that has always been the beginning of something new. Understanding the universe's origins has been one of humanity's deepest preoccupations throughout recorded history. Different cultures developed creation myths that reflected their understanding of the natural world and their place in it. The scientific approach to this question, using observation and mathematics to trace the history of the cosmos, is relatively recent, emerging fully only in the 20th century. But it has produced an account of cosmic origins that is, in many ways, more astonishing than any myth, because it is constrained by what the universe actually did rather than by what we find emotionally or philosophically satisfying. The scientific account says that 13.8 billion years ago, all the matter and energy in the observable universe was compressed into a region smaller than an atom. From that extraordinary state, it expanded and cooled over billions of years to produce everything we see. The carbon in our bodies was forged in the interiors of stars that were born and died before the sun existed. The oxygen we breathe was produced in massive stars that exploded as supernovae, scattering their enriched material through the interstellar medium where it eventually became part of the nebula from which our solar system formed. The iron at the Earth's core came from similar sources. We are, in the most literal scientific sense, made of stardust. Our atoms have been through the cores of multiple generations of stars. The hydrogen in our bodies is the primordial hydrogen that emerged from the Big Bang itself. Every time we breathe, we are cycling ancient hydrogen through our lungs. Every heartbeat pumps iron that was forged in a stellar explosion billions of years ago, in a star that we will never see because it died before the sun was born. This is the context in which the early universe observations from Webb take on their full significance. When we ask when the first galaxies formed and how massive they were, we are asking about the early chapters in the story of how the matter that makes up everything, including us, came to be organized into stars, planets, and eventually, living beings capable of studying the night sky. The first galaxies were the factories where the first heavy elements were produced. They were the engines that transformed the primordial hydrogen and helium of the Big Bang into the chemical richness that makes complexity possible. Understanding them is not an academic exercise disconnected from human experience. It is an investigation into our own origins, several generations of stellar ancestors removed but unambiguously part of the same story. What Webb is finding about these earliest factories is that they were more productive than expected, more efficient, more rapid in their work. They seem to have been running harder and faster in the universe's first few 100 million years than our models said they should have been. If that is true, then the chemical enrichment of the universe began earlier than we thought. The raw materials for planets and eventually biology were available sooner than the standard timeline suggests. This does not mean that life necessarily appeared earlier in other parts of the universe than our models predict. The path from chemical enrichment to habitable planets to life is enormously long and involves many steps we do not yet understand. But it does potentially extend the window during which life could have been possible, a fact that bears on some of the deepest questions about whether we are alone in the cosmos. These questions about life in the universe are not primarily what Webb was built to address, but they are connected to its observations through the chain of reasoning that links early galaxy formation to chemical enrichment to the eventual emergence of the conditions for biology. Webb's discoveries, by potentially revising the timeline of the universe's chemical history, have indirect bearing on the question of when and how frequently the conditions for life might arise in the cosmos. The questions Webb is raising also connect to fundamental debates in the philosophy of science about the nature of cosmological models and how they should be evaluated. Lambda CDM is not a simple theory that makes predictions one at a time. It is a comprehensive framework that simultaneously makes predictions about dozens of different observational properties of the universe. When one set of predictions fails, it does not immediately invalidate the entire framework, because the other predictions may still be satisfied. The question of how to weigh evidence for and against such a comprehensive theory, how to decide when anomalies reach the threshold of requiring a fundamental revision versus being addressed by more modest modifications, is a genuine methodological challenge. Cosmologists are navigating this challenge in real time with the data Webb is providing. The community is appropriately cautious about drawing strong conclusions from early observations that have not yet been fully confirmed. Spectroscopic confirmation of photometric redshift estimates is taken seriously before theoretical implications are drawn. The possible systematic errors in Webb's calibrations and the statistical uncertainties in small galaxy samples are carefully considered. Alternative explanations for anomalous observations are thoroughly explored before resorting to modifications to fundamental theory. This caution is not timidity. It is the proper scientific response to preliminary observations in a domain where the stakes, the potential revision of fundamental cosmological theory, are very high. The history of science contains many examples of apparent anomalies that turned out to have mundane explanations, and only a few of observations that genuinely required fundamental theoretical revision. The process of distinguishing between these cases requires exactly the kind of careful, skeptical, multi-method analysis that the astronomical community is applying to Webb's results. At the same time, the caution is not infinite. The statistical evidence for an excess of massive early galaxies is accumulating across multiple independent surveys and observing programs. The spectroscopic confirmations are becoming more numerous. The theoretical explanations that do not require fundamental revision of Lambda CDM are being tested and found to account for some, but not all, of the observed excess. The community is converging, slowly and appropriately, on the assessment that something real and significant is being revealed. The pace of progress in this field is also accelerating in ways that were not possible even a decade ago. The combination of high-performance computing that enables detailed cosmological simulations, machine learning techniques that can efficiently classify and analyze large datasets, and the global network of collaborating scientists who can share data and analysis methods in real time, means that the path from raw observation to published scientific result is dramatically shorter than it was for previous generations. The specific numerical models that need to account for Webb's observations are being run on supercomputers that simulate the formation and evolution of galaxies from the earliest epochs to the present day. These simulations, starting from specified initial conditions shortly after the Big Bang, evolve dark matter and ordinary matter under the influence of gravity, hydrodynamics, star formation, supernova feedback, black hole growth, and active galactic nucleus feedback. The most sophisticated of these simulations, projects like Illustris TNG, Eagle, and Simba, have been extraordinarily successful at reproducing the statistical properties of galaxies in the nearby universe. But these same simulations, when extended to the earliest epochs, produce galaxy populations that are less massive and less luminous than what Webb is observing. The discrepancy is being quantified carefully, and teams around the world are running new versions of these simulations with modified physics, exploring whether changes to the star formation efficiency, the feedback prescriptions, the initial mass function of stars, or the nature of dark matter can bring the simulations into agreement with the observations. This interplay between observation and simulation is one of the most powerful tools of modern astrophysics. Observations provide the constraints that simulations must satisfy. Simulations provide the theoretical predictions that observations can test. When they disagree, the disagreement points toward missing or incorrect physics. When they agree, it builds confidence in both the theoretical framework and the observational results. The current disagreement between Webb's early galaxy observations and the predictions of current simulations is therefore not a cause for alarm. It is an opportunity. It is pointing toward specific aspects of early galaxy formation that our current models are getting wrong. And working out exactly what those aspects are will advance our understanding of the physical processes that shape galaxies. This is the scientific enterprise at work. Not a static body of knowledge waiting to be administered, but a living project of inquiry, constantly being extended, challenged, and revised by encounter with nature. The universe does not care what our models predict. It does what the physics demands. Our job is to figure out what that physics is, and the universe provides us with the data we need to do so if we build the instruments sophisticated enough to gather it. The James Webb Space Telescope is the most sophisticated instrument humanity has yet built for the specific purpose of gathering that data from the universe's earliest epochs. What it is returning to us is both confirmation and challenge. Confirmation that the broad outlines of our cosmological picture are correct, and challenge in the details of what happened when the first structures formed. Meeting that challenge will require new observations, new theoretical work, and probably some new ideas that have not yet been thought of. Science at the frontier is always like this. The questions become more refined as knowledge advances, but they do not become simpler. The universe is not running out of surprises. As our instruments improve, and our theoretical tools sharpen, we find that the reality we are probing is richer and more complex than the version we had previously understood. The early galaxies that Webb is detecting at the edge of the observable universe were there all along, shining their ancient light across billions of years, waiting for someone to build an instrument sensitive enough to see them clearly. Now that we have built that instrument, and now that we are looking, they are telling us things we did not know. Some of those things fit neatly into what we already understood, others do not. The ones that do not fit are the most important. They are the universe's way of telling us that our understanding is incomplete. And in science, that incompleteness is not a failure. It is the engine that drives the entire enterprise forward. We are at the beginning of the Webb era in astronomy. The telescope has years, potentially decades, of productive life ahead of it. The observations it has already made represent only a small fraction of its eventual contribution to our understanding of the cosmos. The early galaxy anomalies it has revealed will be studied, debated, and eventually resolved into either a modest extension of existing theory or a more fundamental revision. Either way, our picture of the universe's origins will be more accurate after that process than it is today. And the next generation of telescopes, building on what Webb has found, will push the frontier further still. They will observe the universe at even earlier epochs, look for the very first stars rather than just the first galaxies, probe the detailed physics of reionization with greater statistical power, and test the predictions of whatever theoretical framework emerges from the current period of productive challenge. The universe has been here for 13.8 billion years. The scientific study of its origins has been underway for about a century. We have learned an enormous amount in that time, but the frontier is wider and more interesting than ever. The James Webb Space Telescope has opened a new chapter in that investigation, one that will keep astronomers, cosmologists, and physicists occupied for many years to come. That, in the end, is the most important thing to understand about what Webb is finding. Not just the specific anomalies and the specific challenges they pose to specific models, but the deeper truth that the universe, at every scale and every epoch, continues to be more surprising, more complex, and more fascinating than our most careful theories predicted. That is not a problem. That is the best possible news for anyone who cares about understanding where we come from and why the universe is the way it is. The ancient light collected by Webb's mirrors carries messages that were sent before the Earth existed. Reading those messages accurately, understanding what they reveal about the universe's earliest moments, is one of the great intellectual projects of our time. It is well underway, and the early returns are, as they so often are when human curiosity meets the universe's deeper reality, astonishing. There is another dimension to these discoveries that deserves attention, which is the way in which they are reshaping not just our scientific understanding, but our relationship to the idea of cosmological knowledge itself. For most of human history, the question of what happened in the early universe was not a scientific question at all, because there was no method by which it could be investigated empirically. It was a philosophical and theological question, one that different traditions answered in different ways without the possibility of experimental adjudication. The development of modern cosmology in the 20th century transformed this question from one that could only be speculated about to one that could, in principle, be answered by observation. That transformation was itself remarkable. The idea that we could look at the faint microwave glow filling the sky and extract from it precise measurements of what the universe was doing 380,000 years after its birth is not an obvious one. The idea that we could observe the light from galaxies that formed when the universe was less than 5% of its current age, and use those observations to test models of the first fractions of a second of cosmic history is even less obvious. And yet, both of these things are now possible. Webb is extending this reach even further. By observing galaxies from the universe's first several hundred million years and comparing their properties to theoretical predictions in detail, Webb is functioning as a probe of the conditions that prevailed in an epoch we will never be able to observe directly. The first fraction of a second, when inflation occurred, when the fundamental particles of matter first appeared, when the basic structure of the universe was set, left its imprint on the statistical properties of the large-scale structure that grew from it over billions of years. Webb's observations of early galaxies are sensitive, in a statistical sense, to those primordial imprints. This is one of the most profound aspects of modern cosmology. The universe's observable features today carry encoded information about its earliest moments, and by observing those features carefully enough, we can read that information. The cosmic microwave background is the most direct record we have of conditions in the early universe, but it is not the only one. The distribution of galaxies and their properties constitute an independent record, one that has been processed and transformed by billions of years of cosmic evolution, but that still contains traces of the initial conditions. Webb's contribution to reading this record is qualitatively new. Previous observatories gave us statistical surveys of galaxies in the early universe, but limited ability to study individual objects in detail. Webb gives us both, the statistical power of surveys and the detailed characterization of individual galaxies. It can measure the chemical composition of the gas in distant galaxies through spectroscopy. It can resolve the spatial distribution of star formation within early galaxies through high-resolution imaging. It can track the growth of individual star-forming regions over cosmic time by comparing galaxies at different redshifts. This combination of capabilities is what makes the current moment so scientifically rich. The anomalies that have attracted the most attention, the excess of massive early galaxies, are important, but they are only the most dramatic of many ongoing scientific investigations that Webb is enabling. The telescope is simultaneously advancing our understanding of galaxy evolution across all of cosmic time, the formation of stars and planetary systems in nearby galaxies, the atmospheres of exoplanets in our own cosmic neighborhood, and the fundamental structure of the universe through its wide-field cosmological observations. The exoplanet observations are worth mentioning even in this context about the early universe, because they represent another dimension of the same fundamental question: what kind of universe do we live in, and what is possible within it? By observing the atmospheres of planets around other stars and searching for chemical signatures that might indicate biological processes, Webb is contributing to our understanding of whether the universe regularly produces the conditions for life or whether our situation is rare and unusual. Early results from Webb's exoplanet atmospheric studies have already detected carbon dioxide, water vapor, sulfur dioxide, and other molecules in the atmospheres of giant planets orbiting other stars. These are preparatory steps toward eventually characterizing the atmospheres of smaller, potentially habitable planets, a goal that will require long observations and careful analysis over the coming years. The connection between the early universe observations and the exoplanet observations is not just that the same telescope is doing both. It is that both are parts of the same grand investigation into the nature and history of the cosmos. The early universe shaped the conditions that made stars, planets, and life possible. The exoplanet observations are exploring the products of that early universe processing. Both contribute to our understanding of where we came from and how unusual or ordinary our situation might be. This breadth of scientific impact is what makes Webb so valuable and what makes the current period so exciting for astronomy. The telescope is addressing fundamental questions at every scale, from the birth of the first galaxies to the atmospheres of individual planets, and doing so with a level of detail and precision that was simply not achievable before its launch. The scientific community that is working with Webb's data is also a remarkable thing to consider. Astronomers and cosmologists from dozens of countries and hundreds of institutions are analyzing Webb's observations, publishing papers, attending conferences, and building the collective understanding that will emerge from this era of astronomical discovery. The collaboration is genuinely global, enabled by the open data policies that make Webb's observations publicly available, and by the communication technologies that allow scientists on different continents to collaborate in real time. This global scientific community is itself a product of the same historical processes that produced modern cosmology: the slow development of international scientific cooperation, the establishment of common standards and methods, the creation of institutions that support long-term scientific projects like Webb, and the training of generations of scientists who carry forward the accumulated knowledge of their predecessors while pushing at the frontiers of what is known. Science is a social enterprise as well as an intellectual one. The insights that are emerging from Webb's observations do not come from isolated individuals working in private. They come from large, diverse, interconnected communities of researchers who challenge each other's ideas, check each other's calculations, and collectively refine the understanding of the phenomena they study. This social dimension is not incidental to the scientific enterprise. It is constitutive of it. The self-correcting character of science, its ability to overcome individual errors and biases through collective scrutiny, depends on the existence of exactly this kind of global, interconnected community. The early galaxy anomalies that Webb is revealing are being subjected to exactly this kind of collective scrutiny. Multiple groups have analyzed the data using different methods and arrived at consistent conclusions. Alternative explanations have been proposed and tested. Some have been ruled out by follow-up observations. Others remain viable. The community is converging on a clearer picture of what the data actually shows and what it means, through a process of discussion, argument, and ever more precise analysis. That process will continue for years. It will produce papers, conferences, new observations, revised simulations, and eventually a more complete understanding of the early universe than we currently have. The path is not straight, and the destination is not yet clear. But the direction of travel is forward, toward greater knowledge and deeper understanding. This is what the investigation of the early universe through Webb represents at its most fundamental level. The continuation of a project of inquiry that is as old as human curiosity and as modern as the most sophisticated technology we have ever built. The questions have been refined over generations. The tools have been improved beyond recognition. The methods have been formalized and made precise. But the underlying impulse, the need to understand where everything came from and how it came to be as it is as ancient as the first human who looked up at the night sky and wondered. We are still that wondering species, building ever more powerful instruments to extend the reach of our wondering, and the universe continues to respond to our questions with answers that are stranger and more wonderful than what we had imagined. The anomalous early galaxies that Webb has found are the latest in a long series of cosmic surprises, and, like all the surprises before them, they will eventually give way to understanding that makes the universe seem richer, more complex, and more interesting than it did before. That is the trajectory of science. That is what awaits us on the other side of the questions Webb is raising. Not just answers, but better questions, and the tools to pursue them. There is one more thread worth pulling on, which concerns the specific claim that some Nobel Prize-winning physicists are beginning to question whether the universe even had a beginning at all. This is a statement that gets made in popular discussions of cosmology, and it deserves to be examined with some care, because the scientific reality is more nuanced than the dramatic framing suggests. When physicists discuss the possibility that the universe might not have had a beginning, they are typically talking about a specific technical problem, the status of the Big Bang singularity within quantum cosmology. General relativity predicts a singularity at the beginning of the Big Bang, a moment of infinite density and infinite curvature at which the theory breaks down. This breakdown is widely understood to indicate that general relativity is incomplete. Not that no physics was happening at that moment, but that we need a theory of quantum gravity to describe it. Several approaches to quantum cosmology have been developed that suggest ways in which the singularity might be avoided. In Hawking and Hartle's no-boundary proposal, the universe has no initial boundary in time, any more than the surface of the Earth has a boundary at the North Pole. The North Pole is just a regular point on the Earth's surface, not an edge or a beginning. In this model, asking what happened before the Big Bang is like asking what is north of the North Pole. The question does not have an answer because there is no before. Time itself emerged along with space and matter in the quantum birth of the universe. Other approaches, like loop quantum cosmology, suggest that when matter reaches a certain maximum density set by quantum gravity, the attractive force of gravity reverses and becomes repulsive, bouncing the universe into a new phase of expansion rather than collapsing to a true singularity. In this picture, our Big Bang was a big bounce from a previous contracting phase, and the universe has been cycling through contractions and expansions, possibly forever. Physicist Roger Penrose, who won the Nobel Prize in Physics in 2020 for his work demonstrating mathematically that singularities are unavoidable in general relativity under certain conditions, has in recent years been advocating for a cosmological model he calls conformal cyclic cosmology. In this model, the universe goes through cycles called aeons. Each aeon begins with a Big Bang-like explosion and ends with an infinite dark future in which all matter has decayed or been consumed by black holes. The very distant future of one aeon becomes, through a mathematical transformation involving conformal rescaling, the very beginning of the next. Penrose has claimed to see signatures of events from the previous eon in the cosmic microwave background, though these claims remain highly contested. James Peebles, who won the Nobel Prize in Physics in 2019 for his theoretical contributions to physical cosmology, including foundational work on the cosmic microwave background, dark matter, and large-scale structure, has been more measured in his statements. Peebles has emphasized the importance of treating the Lambda CDM model as a working framework that should be continuously tested against observations rather than as a settled truth. He has pointed out specific aspects of the model that he regards as poorly justified or in need of better observational support. But his position is not that the universe had no beginning or that the Big Bang did not happen. It is the properly scientific position that our best current model should be held with appropriate uncertainty and tested rigorously. The broader point about whether the universe had a beginning is one that remains open in a technical sense, because we do not have a theory of quantum gravity that can describe the moment of the Big Bang itself. What happened at and before the singularity is genuinely unknown. Different theoretical approaches give different answers, and none of them has yet produced observational predictions that have been confirmed. This is not a failure of science. It is an honest acknowledgement of the current limits of our knowledge. What Webb's observations connect to, in this context, is the slightly less extreme question of what the universe was like in its first few 100 million years, not the moment of the Big Bang itself, but the earliest period from which we can observe galaxies. And what it is showing is that even this much more recent epoch is less well understood than we thought. If our models of galaxy formation, which rely on physics that is much better established than the speculative theories of quantum cosmology, are already challenged by what Webb is finding, that is a signal to take seriously. The challenges are not about whether the universe began. They are about whether the specific story we tell about how it evolved in its earliest accessible epoch is complete. And the answer, increasingly clearly, is that it is not. Something about the physics of early galaxy formation is missing or incorrect in current models. Working out what that something is, that is the task now before the astronomical and cosmological community. And it is a task that, for all its difficulty, is being approached with the best tools ever assembled for the purpose. The James Webb Space Telescope is collecting light that was emitted when the universe was less than 1 billion years old, light that has been traveling for most of cosmic history to reach our detectors. Every photon that lands on Webb's mirrors is a message from a time and place unimaginably distant from our ordinary experience, encoded in wavelengths and intensities and polarizations that carry information about the physical conditions of the universe in its youth. Decoding those messages, comparing them with what our theories predict, revising our theories when the predictions fail, and testing the revised theories against new observations. That is the cycle of scientific progress as it applies to the study of the early universe. It is slow by the standards of everyday experience. A single paper can take years from initial observation to published result. The resolution of a major theoretical debate can take a generation of researchers. But by the standards of the questions being asked, questions about the origin and evolution of the entire cosmos, it is extraordinarily fast. Within living memory, we did not know whether other galaxies existed beyond the Milky Way. Within living memory, we did not know the universe was expanding. Within living memory, we did not have precise measurements of the cosmic microwave background. And within the last few years, we have gained the ability to observe individual galaxies from the universe's first few 100 million years in detail that would have seemed impossible to the founders of observational cosmology. The pace of progress is accelerating. Each generation of astronomical instruments, each improvement in computing power, each advance in theoretical understanding adds to our ability to ask and answer these questions. The James Webb Space Telescope represents the current peak of that accumulated progress. What it is finding at the edge of the observable universe is a challenge and an invitation, a signal that our story of cosmic origins is incomplete and that the work of completing it is well underway. The early galaxies at the edge of Webb's observational reach, too bright and too massive for the time in which they appear, are not anomalies that undermine science. They are data points that science must account for. And accounting for them, working out the physics that produce them, will deepen our understanding of the universe in ways that we cannot fully predict from our current vantage point. That unpredictability is itself one of the things that makes science exciting. If we already knew what we would find, there would be no need to look. The fact that the universe continues to surprise us, that even our best theories, refined over decades against an enormous body of observational data, still fail to predict what the James Webb Space Telescope is seeing in the early universe, means that there is still genuine discovery to be made. The frontier is still open. The most interesting questions are still unanswered. And somewhere in the data that Webb is collecting, in the spectra of ancient galaxies, and the statistics of their distribution across the early universe, is information that will help answer those questions. The work of extracting that information is ongoing. The scientific community is engaged with it, debating it, analyzing it, publishing papers about it, and building the collective understanding that will eventually resolve the current puzzles and reveal the next ones. That is the story of science as applied to the deepest questions about the cosmos. An ongoing conversation between observation and theory, between what the universe shows us and what our models predict. Driven forward by curiosity and constrained by evidence, producing an ever more accurate and ever more surprising picture of the reality we inhabit. The James Webb Space Telescope is the latest, most powerful instrument in that conversation. What it is saying, through the ancient light it collects from the edge of the observable universe, is that the conversation is far from over. The universe has more to tell us. We are only beginning to listen.